Hello, I'm your green instructor. This is our first lecture in dimensional analysis. The objectives: we want to understand what dimensional analysis is, know what a ratio is and how to form ratios, know how ratios and dimensional analysis are related, and know what a conversion factor is and how to form conversion factors. Okay, here is dimensional analysis basics. Exactly what is dimensional analysis and what is it good for? Dimensional analysis is simply the process of analyzing the units to help solve a problem. It makes use of conversion factors and it makes sure that the answer has the correct units. First, we need to review ratios. A ratio is just a comparison between two objects. It doesn't matter what the objects are, as long as you are comparing them. The comparison can be expressed using division notation. So in order to understand dimensional analysis, you need to understand how to perform division, and it'll be you need to know how to um, handle fractions. Here's an example. Let's say that we have 16 girls and 8 boys in a classroom. The ratio of boys to girls is 16. The ratio of girls to boys is 16 to 8, or 16 divided by 8. The ratio of boys to girls is 8 to 16. There are 8 boys for every 16 girls. Now these ratios are equivalent. Here we have the number of girls in the numerator, and down here we have the number of boys in the numerator. Sometimes ratios are expressed using a colon. Now, using our 16 girls and 8 boys example from the previous slide, the ratios would be expressed as 16 colon 8 for the ratio of girls to boys, and 8 colon 16 for the ratio of boys to girls. So you may have already seen ratios expressed using the colon notation. However, for dimensional analysis purposes, the colon notation is not useful and we're not going to use it. Well, what's the purpose of ratios? The purpose of ratios is to make comparisons. If the ratio is a proper fraction, then the number of items in the numerator is less than the number of items in the denominator. In this case, the value of the ratio is less than 1. So if you remember, a proper fraction is just a fraction where the numerator is less than the denominator. So for example, 1/2 is a proper fraction because 1 in the numerator is less than 2 in the denominator. Now, if the ratio is a proper fraction, then the number of items in the numerator is larger than the number of items in the denominator. This time, the value of the ratio is greater than 1. For example, 7/3 is an improper fraction because the numerator is 7 and is larger than the 3 in the denominator. Now, in our example, the number of girls is greater than the number of boys. To be exact, there are 2 girls for every 1 boy. We could also say that there are half as many boys as there are girls. Okay, let's look at the connection between ratios and dimensional analysis. So we want to know, what do ratios have to do with dimensional analysis? Well, by including the actual object names in the ratio, we form conversion factors. And dimensional analysis surely uses conversion factors. Let us rewrite our girls and boys ratios and include the object names. Over here, instead of writing the ratio of just 16 to 8, we're going to include girls in the numerator and boys in the denominator. So the ratio 16 divided by 8 has become a conversion factor. Now it is 16 girls divided by 8 boys. Or we can form another conversion factor with the same two pieces of information. The two pieces of information that you probably were given that you had to use to form conversion factors, you were probably given 16 girls and 8 boys. So in this conversion factor, we put the 8 boys in the numerator and the 16 girls in the denominator. Thus, we have a new conversion factor. Now notice we have the same two pieces of information, but what was originally in the numerator has become the denominator, and what was originally in the denominator has become the numerator. Thus, the objects of interest, girls and boys, are now included in the ratios. By including the objects of interest in the ratios, we form conversion factors. So some people say conversion ratios. Now, it's very important to realize that these two conversion factors are equivalent conversion factors. Now, we didn't say that they are equal, but they are equivalent. Which one you use depends on the problem statement. It depends on what you're given first, and it depends on what you're trying to find. Again, this is pretty much one of the most important concepts to understand when we actually want to use dimensional analysis to solve problems. So we can make two equivalent conversion factors from the same two pieces of information. Now, sometimes you'll be given the conversion factor, for example, 12 inches per foot, but sometimes you have to form the conversion factors. So now you're prepared for the case where you don't have the conversion factors given. Okay, below we show how to form two different conversion factors from various objects. So here we have 1, 2, 3, 4, 5, 6, 7 stars and 2 moons. So we can form the two equivalent conversion factors, 7 stars divided by 2 moons, or equivalently 2 moons divided by 7 stars. Here we have 1 fish and 1 chipmunk. So the two conversion factors are 1 fish divided by 1 chipmunk, or 1 chipmunk divided by 1 fish. And down here we got 1, 2, 3, 4, 5 suns and 1, 2, 3, 4 clouds. The two equivalent conversion factors are 5 suns divided by 4 clouds, or 4 clouds divided by 5 suns. Now we can write ratios and conversion factors for any two objects. It doesn't matter how many of each object we have, and it doesn't matter what the objects are. However, some ratios are special and are actually commonly used conversion factors that are used to solve everyday problems. The ratio involving centimeters and meters is one such special ratio. There are 100 centimeters per meter. Equivalently, we can say that there is 1 meter per 100 centimeters. The word per simply means to divide. Therefore, when we see 100 centimeters per meter, we write that statement as 100 centimeters divided by 1 meter. So 100 centimeters per, meaning this horizontal bar, which means divide, meter, 1 meter in the denominator. So the equivalent conversion factors are 1 meter divided by 100 centimeters, or 100 centimeters divided by 1 meter. Now, let me share the dimensional analysis motivation with you. Dimensional analysis is not part of the Common Core standards for 5th grade math. In my 5th grade, my 5th grade green math textbook that I wrote, dimensional analysis is added to the textbook because I truly believe that dimensional analysis should be introduced in the 5th grade, and waiting beyond the 5th grade is a disservice to our students. On my website, there is a series of lectures on 5th grade math. Now, other 5th grade math books teach ratios, proportions, and rates to solve the types of problems that dimensional analysis alone can solve. Because dimensional analysis is such a valuable skill and one that is not hard to master, waiting to introduce it at a later time after the 5th grade is truly, in my view, a disservice to students. Dimensional analysis can be used to solve many types of problems. It can be used to solve science, business, engineering, surveying problems. They all make use of measurements and or have to convert from one type of unit to another. So this is where the beauty of dimensional analysis comes in. It makes the conversion so much easier and much less prone to errors. Summary: dimensional analysis is analyzing the units to help solve a problem. So in dimensional analysis, when we start doing some examples, we're going to see that the first thing we do is we analyze the units and make sure the units come out correctly in the answer before we start tackling the number part of the answer. If you start tackling the number part of the answer, then you kind of circumvented the objective. A ratio is a comparison between two objects. Ratios are used to make comparisons. And by including the actual object names in the ratios, we form conversion factors. And dimensional analysis uses conversion factors. Per means to divide. The reason that I've wanted to wait until the 5th grade to introduce dimensional analysis is because we need to know how to divide, and we need to be comfortable with fractions. Here are some practice problems. But thanks for your attention, and we will see you at lecture number 2. Goodbye.